x is not equal to x dashed, right? When x is not equal to x dashed, this delta takes the value 0, right? So it's just 0 everywhere along the x-axis, except at one point, which is x dashed. That's a constant position. It's a point along the x-axis, x dashed. Its coordinate is x dashed, right? And the value of this delta then is infinity when x actually equals x dashed. Okay, so it's a bi-valued, a two-valued function, naught and infinity, with a restriction that this function, if you integrate this function over the limits a to b, now provided that your x dashed here, this constant here, lies within the range of a and b. Okay, otherwise it's not much point. Okay, so assuming this x dash lies within the limits of a and b, these are just constants, two points somewhere along the x-axis, and here's your x dash between these two somewhere. Okay, and so this is just saying that the area under this curve, this function here, is 1. Okay, like I was saying before, and where your x dash has to be within these two limits. All right. Now, given that, can you see the following? Does this make sense to you? If you integrate some arbitrary function f times the delta function dx, over limits a, b, can you see that this will just be f of x dashed? Does that seem intuitively obvious to you? Because go back to your high school, I guess. Go back to your high school calculus. What is an integral? It's a sort of sum, right? It's a sum of a lot of rectangles, right? To get the area under the curve, you approximate. This integral is the limiting sum of the area of rectangles. So think, replace this integral sign by the sigma, and then you're talking rectangles, the area of rectangles, and this here would be the width of each of these little, very, very thin rectangles, delta x. But this here is 0 for all these rectangles except where x equals x dashed. Okay, so then the height here would be f of x dashed, and that's the only rectangle that counts. Okay, so I hope it's sort of intuitively obvious to you that this integral is just f of x dashed. So in a sense, this delta function is sort of plucking out one value of f of x, and at a particular value of x, namely x dashed. Right? So you get that. Now I put a star here because we're going to use this a bit later. All right. Now there are some three results here. I asked you to do it for homework. For homework, prove these three results, and the method of doing that is multiply both sides in all three cases, three different identities, three different equations, by multiplying, that's what that means, xing, multiplying both sides by f of x, and then integrating. Right? So sort of like this, integrating like that. Okay. So here your x dashed is 0. Right? So when x equals x dashed, you'll get this. It's not too difficult. Just do that as a homework exercise. Right? Now a few more results. Now this is 2 pages in the appendix. Remember, Appendix C. So you expect a bit more detail. Now I don't know if you've ever heard of something called the Heaviside step function. Heaviside, he was a British applied mathematician, very keen. He liked very much Maxwell's equations, and he was a member of a school of thought in, I think, London. Not too sure about that. Anyway, in Britain. And there were my memory serves me correctly, I think I came across a book once that Heaviside and others were trying to make models of the ether, mechanical models of the ether to explain the light properties of light that would supposedly propagate through the ether. The idea that Einstein killed off the concept of the ether. And now it's come back again with Higgs, right? The Higgs field that's everywhere. So in a sense a kind of ether, and gives particles their mass. The particles interact with this Higgs field, and the different strengths of that interaction correspond to different levels of inertia of those particles. So it's sort of like particles moving through molasses, treacle, depends on British or American. Very thick, gooey substance, like putting your finger through honey. If you try to move your finger quickly, through honey, you can't. There's a resistance because the honey is very sticky, viscous. I think the technical word is. Okay. Anyway, all right. So this is the same Heaviside, and he, despite all the wonderful things he did in his life, he's known for something really simple. That's often the case for mathematicians, and Dirac, one of the great quantum mechanics, and he's known for his name is attached to quite a few labels. But here's an example. The delta function is pretty trivial, right? Well, similarly for the Heaviside function. Now, the Heaviside function and the delta function are related. What is the Heaviside function? Well, it's just, here's the essence of the concept. It's just a step function, right? So imagine here's the x-axis, and the Heaviside function is 0 until it reaches the point x dashed, and then it shoots up to 1. So it's a step, just like a step on a stairway. So 0, 0, 0, 0, and then whoop, goes up to 1 and stays at 1. Okay, so it steps up at position x is x dashed. Okay, so it's a function. The Dirac function is a spike, whoop, whereas the step function it just stays there. Once it jumps up, it just stays there. Now, probably intuitively you can see that if you derive and take the derivative, if you differentiate, take the derivative of the Heaviside function, you get the delta function. Yeah, they're related in that sense. Now, how do you prove that? Well, here's your Heaviside function, defined here, differentiate it, and then put that in this star equation, which is here. Okay, so for f of x here, substitute this d theta by dx. Okay, and if you get this, then that means that if you differentiate theta here, the Heaviside function, and it gives you that, well, that means that this d theta dx must be equal to this. Is that what I'm saying? Sorry. You substitute d theta dx for this, not that. That just stays there. Yeah, sorry. Right? Okay, so let's actually do it. So again, I've asked you to do it for homework. I don't give you every step, but I do about half of it, so make it easier. Right? So for the delta function, substitute d by d Heaviside dx. This f of x. You can integrate by parts, right? So du dv. So you'll just get, when you integrate by parts, you'll get theta f over these limits, which works out to be this. Now I skipped a line or two there, but I hope that's fairly obvious. It's just undergrad or even high school calculus. Okay. So u dv bdx is uv over the limits minus v du. So hence df by dx. Now this is the Heaviside function. So this just becomes df. It's the function of a function when you're integrating. It's high school calculus again. So you get this, and so this just becomes f at these two limits, and you get that as the result. Now it's not, maybe that's not so trivial, but that's left as homework, right? So you do get f of x dashed, which is here, which shows that this and this are the same, right? Because they give you the same result, right? Now 2 bars, so new thought, new concept. Now another way of looking on the delta function. Now I gave you one before, the very thin rectangle, height h, width 1 over h. Well, here's another one. As I said earlier, it has something to do with exponentials. So this definition of the delta function at x equals 0, in fact, because remember the definition of your delta function is here. This is the more general form at a particular point x dashed along the x-axis. And this form, the x dash is just 0. Okay. So in the particular case when x dashed is 0, you get this. And that's the end of the session because I've run out of board. Oh, by the way, you may notice these much thicker crosses here. I can imagine you can guess what they're for. I notice that when I rub out the board to write new stuff on it, I'll often inadvertently rub out these lines, and I've been using those lines to help me orient the angle of the camera, because remember I'm going up and down each time to get so that one rectangle here, 2 squares, fills the frame of the camera. So I don't really need these lines. It dawned on me. I can just do it from these. I suppose you could call them focus crosses. They're crosses used for. Well, the camera focuses automatically, but I guess helping me choose the angle. Like when I'm changing the angle of the camera, like the upper 2 squares and then the lower 2 squares. I found that this is useful, so you'll probably be seeing that more in the future. Now, as the length of the equations gets longer, I may, I'm always experimenting, trying to find new ways, better ways of doing things. After a while, I may just get rid of this division and just write along two squares. Well, there wouldn't be squares anymore; it'd just be the board then would consist of just 4 rectangles. So I'm thinking of doing that after a while. But for the moment, this seems to work. I'm noticing, as I play back videos from YouTube, the final result, and the visibility is good. Right? It's very, very clear. I can write very small stuff and it'll still come out. And when I look at the string theory stuff and quantum field theory and the equations get so long, I'm going to I think I'm just going to need that amount of length just for some of these really long equations. So. Expect that perhaps in the future, but at the moment it's just step by step.